Welcome to another episode of Talking Kotlin, everyone. My name is still Seb, and I'm still here with my co-host Hadi.
Yeah, you still haven't kicked me off yet, right? You keep trying. You keep trying to get rid of me. How's the weather, Seb?
Keep trying and keep failing. It's pretty decent. I hope it'll hold out for my next vacation, which I'm taking in just 2 days. So
you're going from your living room to your bedroom?
Yeah, to the veranda. Just catching some sunlight, hopefully.
Nice. Yeah, it's kind of sunny out here right now, but again, me with my blinds down and having to have lighting and all of that stuff because, well, we're here, we're talking Kotlin, right? And today we're going to be talking Kotlin with two awesome individuals who are Jeffrey and Mads from Google. And we're going to be talking about contributing to the compiler and many other things. So let's welcome our guests.
But yeah, so I'm Jeffrey Van Gogh, an engineering manager on Android Studio, and I'm mainly in charge for Android's programming languages.
And my name is Mads Ager. I'm a software engineer at Google. I'm on Jeffrey's team. I'm the tech lead for some of the compiler stuff that we do. So we're building the D8 dexer that turns Java class files into dex files, the R8 shrinker, which makes Android apps smaller, and most importantly for this podcast, we're working on the Kotlin compiler.
Wow. Yeah, it's really good to have both of you on the show. And I probably just want to start you off with a bit of an open-ended question. And yeah, you can just see where that takes us. You say you're contributing to the Kotlin compiler. What would you say does that entail? Like, what kind of scope is that?
So the main two things that we're working on are the new compiler backend that is coming for the Kotlin JVM backend. We're about to turn it on as the stable for the 1.5 release. And we're also working on the new front end because build speed is a very important issue for all people using a compiler and definitely also for Kotlin. We have some other projects as well. Maybe we should wait a little bit with those, and I'll be happy to dive more into why we're contributing to both the new front end and the new back end. So if we start out with the back end,
so Mads, before we kind of go further, because I know that some people have maybe listened to some previous podcasts of mine, which apart from my mother, of course. And for folks not familiar with the concept, what is the front end and what is the back end? Because I'm thinking people are saying like Kato server and okay, no, JavaScript.
Sure, sounds good, Hadi. So typically a compiler is split into two parts: a front end and a back end. The front end is the part that takes your input source and figures out if it's actually a valid Kotlin program. So it will do a syntax analysis. It will figure out if it even makes sense according to the grammar of the language, and then it will start analyzing whether the what you typed in. Now you know that it's syntactically valid, but is it also sort of semantically valid? So do the types make sense? And for the Kotlin compiler, that involves stuff like resolution, finding out for any symbol what it refers to. It involves type checking, figuring out if all of the types make sense, and if you expect a string to flow somewhere that nothing else flows there, that you don't get a hash table flowing in instead. And since Kotlin does not have explicit type annotations on everything, it also involves like type inference. And then, so basically the front end is what figures out, is this even a valid Kotlin program? If it isn't, it needs to reject the program. If it is, it passes it on to the backend. And the backend then needs to take what it now knows is a valid program and generate the output. So in terms of Kotlin, if you're using Kotlin JVM, that's generating class files that can be run on a Java virtual machine. If you're using Kotlin for JavaScript, it will generate JavaScript code. And if you're using native, it will generate native code.
So is it correct that you folks are working mostly on the JVM backend then, right?
Yes, that's correct. So for the backend work, it's mostly on the JVM backend. So if we dive into the backend a little bit more, the main reason for Google getting involved in that was basically Jetpack Compose. So of course we want the compiler to move forward since we're heavily invested in Kotlin, and we have a lot of happy Android developers using the Kotlin language for their Android apps. But we also had this project called Jetpack Compose, which is a new UI toolkit for Android that just went beta, was it last week or 2 weeks ago? And one of the things that Jetpack Compose does is it has a compiler plugin. And you write your code so that it looks very nice and easy. So you just like write a linear layout, and then you have like a lambda which has children, like X images, and then you build up your UI with something that just looks like a lot of function calls. And then you have an annotation that's called @composable. And that one is where the magic happens, because then the Compose team has a compiler plugin that rewrites all of your composable functions so that at runtime, you will not always sort of compose your full UI. You will only recompose the things that changed. I'm not an expert on Compose, so if any of that is wrong, I really apologize, but that's my understanding of it after anyway. And the current backend, JVM backend, was not very easy to deal with in terms of some of these rewritings. So that's where the new IR, intermediate representation in the compiler, is very useful for us. So actually, Compose never used the current backend. It always used at that time, very young, new backend based on this new intermediate representation. And the bottom line is that intermediate representation is a lot easier to rewrite than the structure in the current backend. And that's why we were really interested in this, because we could see that supporting Jetpack Compose in the current backend would be hard. It would just be difficult, and it would be a lot easier if we could just do it in the new one. At the same time, if we didn't engage and involve and try to help, if we were sort of a little uncertain if our timelines would end up matching. So what we are trying to do there, and what I think we succeeded in, is helping accelerate the development of the JVM version of the IR backend, so that it's now basically ready to go stable in 1.5, which fits very well with Compose having just gone beta, so that we're ready to have a Compose version ship at some point that is based on what is the default compiler backend for the JVM compiler backend.
So just as a small follow-up so that I understand this correctly, you're saying that the compiler plugin that you folks are building, it doesn't really touch your Kotlin code in any way. It just touches this intermediate representation and can figure out based on that what type of like what the intent of the user was when they describe, for example, the user interfaces in this Compose DSL.
Yep, exactly. So it looks at it hooks into the compiler, gets a hold of this intermediate representation. It actually hooks in multiple places, but one of the places it hooks in is in the backend, and then it finds everything that's annotated with this specific annotation, and then it knows what to do from there on. And what it needs to do is actually rewrite the code, and it does that using this intermediate representation. The things that are complicated is that it needs to like add more parameters, deal with having things having the right type, and the current backend is based on sort of a pair of a pure source view of your program and then semantic information on the side about types and all of that recorded by the front end. That means that it's a little hard to rewrite this, because you need to rewrite basically source, like generate new source, and then you need to also update this separate structure on the side, and that's complicated. The new infrastructure is a lot easier, because you basically have something very much like an abstract syntax tree that is then annotated with the type information, and it's much easier to just say, oh, let me add a new parameter over here, and it has this type. So it's much easier to deal with in the new representation than in the old one.
So it's no secret that the compiler plugin wasn't very easy to work with in the past. Have you found that improved and the stability of it?
So at writing the plugin with a new infrastructure has been significantly easier. I think the sort of inherent complexity in leaking out your internal compiler infrastructure, it's one of the things that, to be honest, we've actually resisted in some of our own compilers. So if we talk about like the D8 dexer or the R8 shrinker, we've had requests for like, could you make this a compiler suite where people can write plugins? And so far we've resisted because it does get complicated. And it does so for the Kotlin compiler as well. Jetpack Compose have been doing this very early with the new IR structures. And of course, while it's still early days for a compiler backend, you change the intermediate representation frequently, often, and for good reason. But that means that if you have these plugins that also look at it, they don't live in your own repo, then of course you're breaking those plugins. And realistically, that will continue to happen. Hopefully, a lot less now that we're getting ready to go stable with the new IR backend. But it probably will happen. After all, we are hooking into the guts of the compiler, and if something needs to change or needs to be extended, well, then it kind of has to. And that means that will break compiler plugins. So yeah, it is hard to work with, Hadi. I think it's still relatively hard to work with because we do not have any sort of strict contract that the intermediate representation cannot in any way change. And I don't think we should do that because that would make it very hard to make progress on the Kotlin compiler and the Kotlin language, right? I mean, if you introduce something new in the language, sometimes that's easiest to do if you're also allowed to like add something to your intermediate representation. So that means that that plugins will see something new. So I think it will be. We will continue to be able to have to do changes in the Jetpack Compose compiler plugins as the compiler evolves, and I think that's sort of just the name of the game.
In your explanation of this part, you actually mentioned that you folks are also maintaining a bunch of other compilers, I guess. Do you want to kind of expand a little bit on this? Because, for example, I didn't know that if I run my Android application, that it's gonna run through what are essentially multiple compilers. And more importantly than that, I would actually be interested in kind of knowing, do you have any lessons learned from these other compilers that you're now kind of bringing into working on the Kotlin compiler?
So let's start out with the basics. So the other compilers that I mentioned were D8, which is a dexer. So Android development mainly happens in languages that target the JVM, or in like C++ to ship some native code on your devices as well. For anything that's written in a language that can target the JVM, you end up with Java class files. So that can be Kotlin and Java, which are sort of the supported ones, but you could use a bunch of other things. Like you use Scala to generate class files if you wanted to, or any other language that ends up generating class files that can run on in the Java ecosystem. However, Android phones do not run class files. They have their own format, which is called dex files for Dalvik executables, and that's sort of an old name because the old VM was called Dalvik. Nowadays, it's called Art for the Android runtime. So anyway, the file format that an Android device can execute is called dex files, and they sort of contain similar information as class files, but there's a translation step going on there. So we need to take all of the class files for your app and we need to transform them into dex files. That means that we need to change the representation of metadata for classes, for methods, and for methods there's code as well, and the code in a dex file is not stack-based, it's register-based. And in a Java class file, it's stack-based. So there's a transition there as well. We need to replace Java instructions with sort of equivalent dex instructions. And then there's a register allocation problem there as well, where we need to transform stack-based code into register-based code. So that's sort of the dexer. That is basically a tool to take your class files and transform it into a different language, which can be run on Android phones. So that's one of them. R8 is an application shrinker. So as a part of R8, you actually have D8, because R8 takes your app with a specification of entry points into your app, and then it tries to find things that you don't need and remove it from your app so that your app gets as small as possible. It also tries to optimize your app. So the thing that makes that complicated is reflection, and that's why you need to specify what you're using in your app, because Android apps are not like a command line Java program where you have like a main method and everything reachable from there is reachable. There's a lot of reflection going on Android. Basically everything is reflection. So in an XML file in your Android app, you specify entry points to your app. And those are then basically loaded by reflection. So the system will then say, hey, please find this class and start this activity. So there are a bunch of tools that generate specifications of your entry points. And then as a user, the only thing you have to worry about is if you or one of your libraries use explicit reflection to look up classes or methods at runtime, then you need to specify that for the shrinker as well. And then the shrinker will take the specification of where are the entry points in your program, then it'll find all of the code that's reachable from there. And if there's anything that's not reachable, it will throw it away. It sounds kind of weird to have a bunch of unreachable code in your app, right? But that's actually not that weird in the Java ecosystem, because the way you typically build Java applications is you take all of your library dependencies. Those are jar files, which are basically zips of a bunch of class files containing everything in the library. So you'll basically just bundle all of these things together. So if you use a large collection library, but the only thing you use from there is a hash map, you'll still get sets and linked lists and all kinds of other things in your app, unless there's some tool that removes it, and that tool is R8. So Java apps are typically large because you just bundle all of the class files for your app and all of the libraries it depend on, whether you actually use it or not. That's fine for servers. On Android, it's not so great because Android can be fairly small devices.
So I'm not an Android developer, if that wasn't apparent. I mean, it's even in my Twitter bio. But isn't there another thing which is called Proguard, which does something similar? Is it similar to R8 essentially?
Very much. We actually built R8 as a Proguard-compatible solution for Android. R8 does a bunch of things. So first of all, we do what Proguard does, and we use the same specification language, Hadi. So yes, very much so. It's the same kind of thing. And then in addition to that, our target is Dexcode, and as part of this, we also do desugaring. So another thing that's interesting about the Android ecosystem is that right now, the runtime and the libraries that are on your phone is not updatable, which means that whenever an Android developer writes an app, he can only use features that were available 5 to 7 years ago in the runtime that shipped on 5 to 7 year old Android devices, and the core library. So core library that was shipped with that. And that's of course not great. A lot has happened over the last 7 years in the Java ecosystem. Like there's Java 8 where you could start to use Lambda expressions. You got streams in the core library. And all of those language features come with new instructions in the Java bytecode. And there's no equivalent in the DEX format for some of these. And even if there is, that has not been implemented back in time, of course, because we can't ship a new VM to older devices. So that's where desugaring comes in. So we allow Android developers to use these features, in particular the language features, and then D8 and R8 will desugar that away. For R8, it will just be one invocation. It will do it all in one go. It will shrink your app. It will also desugar language features back in time. So basically replace the new features with old ones. For lambdas, that means instead of generating classes for lambdas at runtime, it'll just generate them at compile time, because there's no mechanism for generating them at runtime in the Android runtime. So it'll generate them at compile time instead. That was a very long answer to, is this sort of like Proguard? And the answer is yes for the shrinking part, and for the optimization part, it's very much like Proguard. And then we've stuffed a bunch of other things in there. That means that we only have to launch one tool, which is good for build speed as well, for doing a whole bunch of things that we need to do in the Android ecosystem.
So I've got a question, and we can come back to these aspects as well in a bit. But I've got a question for you, Jeffrey, because you have another role here, right? Which is you are part of the language committee on the Kotlin Foundation.
It's one of the few times that I still get to do deep technical things. Like I have a large org with many people to manage, but the language committee is one of those guilty pleasures where I get to go really deep and look at the deep language features.
So in essence, what you're saying is that, like many of us, your life is full of meetings otherwise, right?
Oh, yeah. Yeah.
So anyway, can you briefly tell people what this language committee is about?
Sure. So as you remember, 4 years ago at Google I/O, we announced that Kotlin must become an officially supported language for Android. And with that, we also launched the Kotlin Foundation that Google and JetBrains are both participating in. And we want to make sure that the language evolves well. So what we did is we decided to have a single language designer lead, which at the time was Andri, and now it's Ramon at JetBrains. And they have final say over any language feature that gets added to the language. This is nice because it makes sure that we can do rapid development, and we don't have to design by committee. Now, of course, we also want to make sure that the language evolves well, so that people can rely on the language, not to break them when they try to upgrade their compiler. And so to complement the single language designer, we added a committee which reviews only breaking changes and deprecations to the language. And so any new feature that doesn't break anything can be added pretty quickly, but anytime we have to break a language, that has to be a bit more carefully done. And so that's where the language committee comes in. We have a set of guidelines on how to review any proposed breaking changes. And so every couple months or so, we get together virtually and we look at proposed breaking changes, and then we have a discussion and decide if this is number one, a breaking change that we're willing to make, and two, is the timeline correct, and three, do we have tooling to help people move forward?
And the reason I bring this up, because I knew what you were going to answer, kind of thing. Okay, I'm cheating. I knew, but because Mads, you were talking about, when we're talking about the plugin and we're talking about the compiler and we're talking about, let's just hope that things don't break and things like that. Does this fall into the scope of the language committee in terms of breaking changes, or does it not?
No. So there's a couple things that are considered for the language committee. So first of all, we look at changes in the language. Second, we look at changes in the library that ship with the language, like the Kotlin standard library. But then there's a whole bunch of things that we consider out of scope. Any additional third-party library, the compiler API itself, the build plugin API, as well as any experimental feature are excluded for review from the committee. And that's because things has to evolve, right? The compiler, its internal structure, as Mads mentioned, you want to be able to innovate there. And I think it's okay to have some pain for people who build tooling, as long as we don't break our users. Compilers are hard, they're complex systems. If you want to write a compiler plugin, you pretty much have to be a compiler engineer or become one. These are not for the faint of heart. It's hard to build these, and that's why we have other layers, right? If you want to do some code generation, you probably should be looking at the Kotlin symbol processing API instead of writing a full-fledged compiler plugin.
Do you actually want to give people a short rundown of the Kotlin symbol processing? Because I think that's a pretty recent change that you folks were also involved in quite heavily.
So Kotlin is doing an awesome job integrating with the existing Java system, right? It's one of the strengths. Now, of course, the Java ecosystem comes with this thing called annotation processors, which are kind of mini plugins into the Java compiler, which, just like in Kotlin symbol processing, have a limited scope. You cannot access full compiler API, but it gives you enough to reason about symbols and then generate additional code. And it turns out that this is used quite a bit in Android to do meta programming. And the problem with that is that in general, these are not fast, even in the Java ecosystem. But in Kotlin, they're way worse, because Kotlin has to do this trick where it takes the Kotlin code, generates Java stubs that it can then feed to the Java compiler to run these Java annotation processors, and then import the generated code back into Kotlin. So it was this multi-phase step to bring compatibility with annotation processors, which drastically slowed down many builds. And because Android particularly uses these a lot, Android builds that you're using Kotlin and annotation processors were slowing down quite a bit. And so talking between JetBrains and Google, we decided that it was time to come up with a native Kotlin solution to this. And so we built Kotlin symbol processors, which very much in the spirit of annotation processors, but Kotlin has things like properties, delegates, that suspend functions that are not in Java. And so modeling those in annotation processors was always hard. In Kotlin symbol processors, we actually have first-class APIs to model these. And then because we're operating on the Kotlin compiler, we're actually a Kotlin compiler plugin itself for Kotlin symbol processing. We can do things much more performant. We can completely dive into the incrementality of Kotlin. We can do multiple runs in a safe way. And so it provides a much richer and faster API. And then the other thing is, because we're working on Kotlin, written in Kotlin code, we're also ready for doing Kotlin multi-platform. And that's something that we're working on adding right now. You want to be able to do symbol processing. We're generating JavaScript or native code as well. And that was something that was never supported in Java annotation processors.
So this opens the door for Kotlin-specific annotations that I can use no matter where I target, or in common Kotlin code as well. Is that right?
Yeah. So you can imagine that people use annotation processors for things like dependency injection or ORM. You can imagine that somebody writes a Kotlin symbol processor that provides you any of those features across your multi-platform application.
And since we talked kind of about the compilation pipeline beforehand, where do I have to imagine that the symbol processor kind of injects itself or hooks itself in?
Yeah. So we have the current implementation in Gradle, and so it's just a Gradle plugin that will insert itself into the pipeline, and it happens just before the Kotlin compiler is invoked. It uses the Kotlin compiler frontend to build up this semantic model, and then run the annotation, the symbol processor over it, and then generates code, and then that code is fed into the Kotlin compiler.
So, Mads, you said beforehand that there were actually some other projects that maybe we could get into at a bit of a later point. Maybe this is the later point. You want to let us know what you have in store?
Absolutely. One of the projects that I actually wanted to talk about was KSP. So you already brought that up, which is great. The other one that we haven't talked about, though, is the new compiler frontend that's coming. So we talked about the backend and how that was important for Compose, but we didn't talk so much about the backend and the frontend, and why it's important that we get a new one. And it's very important for build speed. So one of the top complaints that we get from Android developers, and I think if you build tools for developers in general, not just Android developers, it's probably one of the main concerns that you'll have anyway, and that's compile time. I think all developers have struggled a little bit with the edit, compile, deploy cycle, and how long that takes in a lot of settings. And Kotlin is definitely not an exception. It's not a secret that the current Kotlin compiler is not particularly fast. So at JetBrains, they've started a project to revamp the front end, and it's showing quite massive speed ups. So on the order of a 4 to 5x increase in front-end speed. So basically cutting your time down to 20% in the front end of what it used to be, which is pretty amazing. And that is obviously going to translate into some really good improvements for end users. On some of the benchmarks that we're tracking, end-to-end compilation, including front-end and back-end, it's twice as fast as it is with the current compiler. And that's pretty neat. So that's definitely something we want. And again, we're sort of following the tactics that we did with the backend as well. If this is something that we want, then we should invest some resources in it and help make sure that we get there as fast as we possibly can, because this would be great for the Android ecosystem, and it would be great for some of the tools that we're building as well. So for Android Studio, for instance, we're building apply changes, which is a way to get your code onto an Android device as fast as possible. And of course, you need to build your actual code before you can ship it to the device. So any compiler in the system is sort of on the critical path for that, including the Kotlin compiler. So we're engaging in that project as well. So one of the things that we've been working on there is based on our experience with the backend IR, we engaged in translating from the front-end IR to the back-end IR. So basically, once the front-end is done, it has its own front-end representation of the code, and now we need to translate that into the back-end representation so that the back-end can take over and generate Java bytecode and class files. So that was sort of the starting point. Recently, we've gotten into helping out with the flip side of the story, basically. So there are a couple of things, right? For a compiler, it should accept valid programs and it should generate working code from it. So that was sort of where we started out with this translation from front-end IR to back-end IR. But the flip side of that is it should also reject invalid programs with good diagnostics and showing you the line and like the exact point where that error is, so that you as the developer can fix it. And that's also driven by the front end. And there are these things called diagnostics, which are used both in a standalone compiler to give you errors and like print like there was this line right here, you had an error, but it's also used in the editor. So used in IntelliJ and in Android Studio to pinpoint problems. So we've engaged on that as well. So make sure that the new front end will generate diagnostics in the same way that the old one did. But of course, it has to be re-implemented when it's a new front end. Similarly, on top of those diagnostics, the IDE, both IntelliJ and Android Studio, have quick fixes. So if you see some of these errors, some of them are fairly easy to fix. So the editor can suggest like, hey, this doesn't look right. Did you mean to do this instead? And those are called quick fixes. And our team is engaging on implementing them as well.
So from the tooling perspective, when you say that the front-end IR is much faster, and you said, I think before, and you said that the front-end part is the part that kind of continuously runs as well when you write code. Does that mean that people can also expect, I don't know, even more snappier diagnostics when they make mistakes, completions, this kind of stuff?
Oh, I hope so. That is definitely one of the goals.
And not just diagnostics, also auto-completion, right? That's completely driven off the front end too.
Exactly. It should hopefully be a good improvement in terms of just using the editor on large Kotlin projects, since the front end is significantly faster. That should translate into significantly faster things in your editor as well.
And the quick fixes that you mentioned, they also operate on this front end intermediate representation?
Yeah, well, they operate on. I think basically they go back to PSI though, because they're integrated in your editor. So at the end of the day, what they need to change is your source code. So they get the errors from the front-end IR infrastructure, and they can look at that, right, and figure out what the error is and what a correct fix might be. And then the actual fix will have to then also be a fix to the actual source code that is currently in your editor. So the answer is yes and no. The quick fix looks at the front-end IR to figure out what's wrong and what to do about it. But then afterwards, it does need to go into the source representation and change the source code to do the actual quick fix.
Mads, you mentioned PSI. Maybe you want to clarify what that is, folks.
Yeah. Very earlier in the podcast, I told you that the old backend had this split between a pure source representation and some semantic information. The pure source representation, that's called PSI. I can't even remember what it is. Program source information, probably.
Structure interface.
Structure interface.
The layer that IntelliJ basically has, right? You're referring to, yeah?
Yeah, and that's used for any language that integrates into IntelliJ, Java, Kotlin, other language, C++.
Cool. So talking about the team, talking about the team. Were we talking about the team? We weren't talking about the team, but hey, here's a nice segue about talking about. Oh my God, Jeffrey, is that a ketchup bottle in your background? Like, talk about segues. Is that Kotlin ketchup?
It is. So I ordered a whole bunch of them. I gave them to the whole team here in Bellevue.
Nice. So, and thank you for not talking about the team, because you brought up the team. So beautiful. It just worked out great. So talking about the team, how do you actually collaborate with the Kotlin team? I mean, is it just normally through PRs on GitHub, or do you have more closer relationship? Do you have meetings? How does that work?
Both JetBrains and Google are distributed, right? So I think JetBrains has people working on Kotlin compiler in St. Petersburg and elsewhere in Europe. And then we're split, the compiler team and Google split between Denmark, where our Mads is, and here in Seattle area, where I am. So we have people contributing from both locations. So many different time zones to cover. So there's a lot of asynchronous communication, PRs. We have a Slack channel. We have, I think, bi-weekly meetings as well between the two different compiler teams at the different companies. And then lots of ad hoc email and other communication as well. Before the pandemic, we would try to sync up around Kotlin conferences and Google I/O as well, of course.
We miss those.
Oh, yeah.
Yeah.
I saw Hadi tweeted recently that he doesn't think people are going to go back to in-person events. I think that may have been sarcasm, but...
Yeah, and everyone's like, no, I'm dying to go back. I'm like, yes, it's called sarcasm.
So, let me ask maybe one more question. I assume that you work a lot with code that Googlers have written. You see a lot of code that maybe JetBrainers have written. Do you kind of notice any kind of difference in style or approach in solutions between the two cultures?
I think, to be honest, on the compiler front, we try to blend in, because if you want to contribute to a project, and you have the attitude that, hey, let me use a different style than everyone else in this project, that's not going to end well for you. I think we largely agree with the style, though, so I don't think there are any big discrepancies in what we would normally do. But of course, we try to not deviate from the style in which the compiler is written, because after all, we want to do good work that ends up being accepted and not get drowned in sort of nitpicky comments in the form of, could you put the brace somewhere else? That's not very productive. So I think we try to blend in, and have basically just looked at the JetBrains source base and try to follow that sort of style for our own contributions.
Worth mentioning that I think we are more like a single team now. Like we of course send lots of pull requests to JetBrains and have people on JetBrains side review them. But it's also now that we're starting to see that when JetBrains folks make a change in some area that people on the Google side are more familiar, that we're getting asked to do code reviews from the JetBrains team as well. So you're starting to see that we're becoming more a coherent team versus it's us versus them.
Yeah, it's funny though that you mentioned code style, because again, I was trying to comply with a code style, and I thought to myself, how many minutes of my life have I wasted in trying to do this? But anyway, cool. Well, we're out of time. Well, we're out of time. We're like way over time. But as I said, when we have awesome people on, we have all the time in the world. This is the beauty about doing a podcast that you say is kind of 30 minutes long, because it could be anywhere between 30 minutes to an hour. It just always works. Thank you for coming on, to both of you, taking the time. And yeah, we'll hope to get you on for some other topics and maybe dive deeper into KSP next time.
Thank you so much for these in-depth answers. That was really insightful. Very exciting.
Awesome. Thanks for having us.
That's mainly Mads going deep.
Anytime.
Thank you.
Take care.
All right.
Bye-bye.
Take care.
Bye-bye.
Bye-bye.
Bye.
Well, that was some exciting stuff, but it's actually time for your favorite part now, Hadi, right?
Yes, it is. Oh, yes. It's time to go gardening. Oh, yeah, I enjoy gardening. It's 5 o'clock at Central European time. Soon to be Central Eastern Europe. No, not Central Eastern European. Central European summertime. And but make sure that you come back next time. Ring that bell.
And hit that subscribe button.
Look, I got a real bell. I got a real
It's
bell.
amazing.
And make sure that you hit the subscribe button and the likes. You know, the other day I saw some thumbs down.
What?
I know.
Don't give thumbs up as well if you like this episode.
Yes. No thumbs down.
More engagement.
Thumbs down is so negative. It's so negative.
Put an emoji in the comments, but only a happy one.
Constructive criticism. Not thumbs down.
Yeah, right.
See you next time.
See ya.